Welcome, I'm Bill Wake. We're here working on the 10th programming language, and we're up to the point of needing to do variables and arrays. We've got a bunch of operations on stacks and numbers and so on, and we've got control structures for if, do while, and repeat until, but we don't yet have variables and arrays. We make heavy use of a data stack, so it's not been a huge barrier, but it's needed for real work. All right. Well, we left off, tried to quickly do the test for loadAddress, and we're getting this. And as I looked at the code just before class, it's like, oh wait, there's no first argument here. So for sure that's wrong. But then it's like, wait a minute, this is totally not testing what we need to. All right, so this is x1 was going to be test address. But really, though, what load address is supposed to, it's not supposed to return the address as secondary. It's supposed to push it. All right, so when you do the name, when you reference a name, it should push its address on the stack. So we call it, but that's not. Well, this assertion is not right. There's no x0 returned that we can compare to. I thought it would just be a no op and it would just let the input be the output. But I also thought, well, let's look at start2d, and notice start2d adds VPC adds 8 to the x0. So x0 is passed in to say, where are you? And it'll point into the word address, the address of the call to load address. Or start2d or whatever, and it has to consciously skip past that address to get to the next cell. All right, and that is what we need too. So, excuse me. So I think what our test should do is it should do a data pop to x0. All right, and that's the value we should be looking at, and that should be x1, well, we should do an add, x1 gets x1 plus 8. Okay, so we come in pointing to the secondary, it should move past it to the contained value, and the contained value is pointed to by x0 plus 8 as it goes in. So the value it pushes on the stack should be the address of the contents of the address of the value. Okay, not the value itself, but the address of it. Okay, so I think this is a better test. It's like it wasn't even good enough to be wrong. It was just off. Okay, let's see if this builds at least. Okay, load address referenced from interpreter tests. We probably forgot to declare it as global as usual. Yep. Load address. Okay. Now, all load address is doing now is just throwing some junk in x0, so no real function. Okay. Load address returns start of memory. Oh, I didn't. Load address returns. Oh, I didn't change the name of the test. Pushes address of secondary. Okay, something should have failed. Interpreter. There it is. Okay, we thought we'd get a 55, which, oh no, we thought we'd get this big thing and we got a 55. Okay, because I think we just returned 55, right? So, pound 77, well, that's a little weird. Oh, it's whatever it came up with. That's probably the first letter of Lily or something. But whatever it is, it's not right. Okay, so I think our first step then, we know x0 is coming in with the address, so we're going to have to add x0 gets x0 plus 8. All right, and then we can just do a data push x0. I think that's all it requires. So we probably could have done this in the last 5 minutes yesterday if we'd done it right. I shouldn't say that till I see it pass. Okay, there it is. 55 hex. Oh, okay, thanks. Okay. So, oh, I don't know why it was 55. It would be 77. Well, the x0, no, the stack would be whatever the stack is, right? So I think it would be pointing to our lilies, maybe to our 0, but I think to our lilies. So it's I don't know, maybe it should be bigger. But it's right now. Okay, at least looks right. Okay, so let's see what loadAddress is doing. Given address of secondary, push the following address. And the input is x0 address of secondary. Okay. Good. So let's make sure that's still good. Oops. How about make? Good. Okay, so that's ready to go. Now, okay, let's keep track of this. I guess so today we created load address that loads address of variable. All right. Now we want to do variable name to define a variable. Okay. And variable name is a meta value. So, well, I guess we'll need a function for that. And that's, I guess I could put that in interpreter. I mean, it's kind of part of that set of things. We got the controls there. Kind of our metas are showing up there. Maybe that's what it really is. But okay, so interpreter tests. Oh no, that isn't there, is it? I guess it would be okay with these others. Interpret in secondary runs. Okay. Yeah, that's a little outside. What else? It's not control. It's not arithmetic. Maybe it's its own thing. Variables, and then variables tests. And let's pull that out. Well, I'll copy and then just cut out anything I don't want. Now this thing referenced something. L factorial, no. L test address is the only thing it referenced. Okay, so we can kill off a lot of this. Now I think that should still compile. Oh, I haven't edited into makefile. Now, do we really need to see like? I guess we probably do. Yeah, print. Okay. Oops. And variables. Should get the stuff from interpreter. Okay. Let's see, we need to do more makefile. Okay. And finally, REPL. REPL is going to depend on variables dot out or load address reference from start and interpreter tests. Didn't I move that? Yes. I think it's the same. Load address. Wait a minute, what's this one? So interpreter test dot out. Should not need that. Okay, good. We got the new test thing in there. Okay, so move load address to variables.s. Move test to load variables tests.s. Okay. All right. Oh, some of this is easier in Swift or Java for sure. All righty. Now we're set for more variable tests. Okay, so we'd like to define variable. I guess I can do that here while I'm sitting here. And variable, meta word that takes the following name and makes a, I think I can use words passive word for it. Okay. Haven't used that a lot, but that's what they call it. So most words are active because they've got functions attached. Variables and arrays are not. All right, but the test, well, let's see. We're going to define, how do we test colon? Compile, colon, so just come on. Okay, yeah. All right. We're going to do some of the same kind of stuff. We need our own little read words. And we'll have to install it. And this dictionary gets 800. I don't know where that is. Okay, but this bit is very similar to what we'll do. Colon writes header to secondary. Okay, it's more than we'll do, but it's similar. Okay, so the test. All right, so we'll put some data in there. We create a secondary area. And then we define test string. Yeah, so I think that's the read word. So let's do name and name. And this is a variable. Test name string final. Okay, so standard product. Copy the test string. To a real input buffer. Where's the input buffer coming from? It could be the real input buffer. Yes, okay. All right, so we're copying the name. Whoops. No, we're even down below C. So we're doing assembly language programming, probably for a few more weeks, and I'll go back to Swift, I imagine. But we're trying to define a programming language interpreter, and we're about, I don't know, 90% through that. But we haven't done variables yet, so we're trying to work up variables. Let's see. This is most similar to Forth, which is it was kind of a popular language when microcomputers first got started, maybe in the 70s into the 80s. Maybe there's probably still stuff running it, but it's not as big as it was anyway. But it uses a stack-based language. So if you want to do 3 plus 4, you do 3, 4, add, and then it pops the two things off the stack and adds them and pushes the result back on. So we haven't really needed variables too much yet, or even wished for them. But we're doing test-driven development, and we're doing ARM64 assembler. So a little different. Come back in a month, and I'll probably be doing Swift. If you don't want to look at this, that's fine. All right. So I'm in variables. So we're trying to test that a variable writes header and variable, I guess. How about and value? And value to secondary. So secondary space is where stuff gets compiled to, basically. So we just created a little space here with some junk in it, and we're going to override the routine that reads words. I don't even know why this 800 is here. System dictionary. We'll have to check into that. All right, but this take over the read address, because the job of what you do is you say variable name, and that creates name as a variable with default value 0. Okay, and this lets us start creating that space. And then input buffer is where we're going to write stuff so we can put a fake name in. We're not running the whole interpreter. We're just trying to run enough of it to get this name parsed in. Okay, now sysdict. Yeah, it's got to be. Oh, maybe that test never really looked at it. Oh, yeah, that's true. It doesn't. I don't think it needs to look at the dictionary. We just need to know that it's pointing to the previous entry. So whatever that is, it'll point to that. Secondary space is where stuff really is happening. Okay, that seems true enough. Oh, colon is still an underscore name. Okay, so we're going to branch to variable. Let me just make a note of that. Turn colon into colon. Okay. All right. So if you branch to variable with this name set up, we expect to find, we want to make sure secondary space is adjusted to the right boundary. So, 8 bytes for the string. I don't think that's any kind of requirement. Okay, but it's okay if it is. But we're going to look in secondary space and make sure the test secondary area. Oh, now wait a minute here. Okay, so secondary space, x1 loads that. x1 gets x1 plus 32. Well, I don't think that's right for us. Okay, so it's going to look like, so normally what it looks like, a dictionary entry is pointer to previous dictionary. Actually, it's name string, pointer to previous dictionary, pointer to named string, and then it's the pointer to routine to run to interpret this entry. And then it's going to be a 0. 0 is default value. Okay, so this is kind of the structure in secondary space. All right, so the named string, oh, well, I could put that down where it's useful, couldn't I? All this stuff really belongs down here. Okay, data, text, okay. Right, so we want to check that okay, so name NAME 0 byte, all that should take, well, that should take one word, right? So I think given the test secondary area we have, I don't think we have to add to it. That name should be right there, I think. Okay, so secondary space is adjusted to the right boundary. 8 bytes for the string. 3 times 8 bytes for the header call. Oh. At the end, secondary space is pointing back past all this stuff. Okay, I got it. 0, 8, 16, 32, and 40 would be here, but I want to say 48. Okay, so we are allocating stuff for the variable. Okay, so 8, well, 1, 4, 5 times 8's 40. Okay, so I think that's right. Okay, now, yeah, we offset plus 8, so we skip past NAME 0, blah, blah. That gets us to the first cell, which is the pointer to the previous dictionary. In that previous dictionary, we just arbitrarily set it to 800. Doesn't matter. Okay. And we're loading the contents. Yeah, we get the address, and then we load the contents. That should be that. Okay, next, dictionary pointer should be updated. So system dictionary should point 8 past the start of the secondary area, right? Because start of secondary is our name. Okay. Also, that makes me realize we don't have enough space in here. Okay. Dictionary pointer should be updated. Yes. Second cell is a pointer to the new string, so it should be equal to LTest secondary area. Third cell points to, and this should point to our load address. You missed 24 when counting. Ooh, make sure. Let me number them. Okay. This is 0. Name has 4 plus 1 for the 0 byte is 5. It's got to be under 8 to be one word. Okay, 8, 16, 24, 32, and then 40 is the next cell. Whoops. Okay, so 8, 16, 24, 32. That looks right now. All right, let's go back here. String was written to dictionary. Okay, oh, we did test that one. All right, good. L variable. Okay, so at x0 plus 0, we did that. Oh, so I think plus 0, this thing should be 40 then? I think that's where you're fixing me up. 1, 4, 5 times 8 is 40. Okay. Okay, so we got the right string. We got the right secondary space. Move past all that. The first cell is the dictionary. The second cell, make sure the dictionary points to the right place. Make sure the header cell points to the previous dictionary. Make sure the dictionary got updated to point to our current cell, which is offset plus 8. The second cell points to the new string. So that should be 16, right? New string 16. Load address X. Okay. Third cell points to load address. That's going to be 24. All right. And then fourth. Okay, so load X0 system dictionary plus 32. Am I consistent here? Yeah. Okay. And then we got to load the contents. X0 gets contents of X0. And then x1, move x1 gets 0 and assert they're equal. Okay, so we're making sure that cell actually contains a 0. Now, this should hopefully not pass. I shouldn't pass, but hopefully it doesn't just blow completely apart. But even if it does, we kind of know why. So, all right, now where's variables? All right, get that in here. And then did I call load address? I need to call variable. Okay, I did. All right. Did I make that global? Yes. All right, so make, boom, expected new line. Oh yeah, I'm misreading that. That's not the values. That's saying 16 cells of 8 bytes each. Okay, so they'll get filled with 0. 16's enough. We only needed 6 or 7. 5 or 6. Input buffer referenced from start in variable tests. Okay, so input buffer. Is it input.s? Okay. Okay, variables tests. Did I not call that thing? There we go. Okay, it's failing for a bit until we get a little further along. All right, x0 equals 0, x1 equals 1. Oh, this is the string. Okay, so the string is not there. Good. It shouldn't be yet. All right, so compile is the thing that did that before, and I think there's probably a method in there we can extract. Compile. All right, so colon, it reads the word, puts the word string where it should, excuse me, adjusts secondary space to the right boundary, puts the old dictionary at the first slot, updates the dictionary, sets the second dictionary to the word we just created, creates the pointer to the start 2D. Well, that's the part we don't want to do. Okay. And then move secondary past the headers. Okay. Let's pull out. I think the code down here is a little more coherent to what's going on. It's defining a word, but if we just take to here. So we haven't put in the third slot. Yeah, I think I'd like to. I want to change. I want to move this around. Okay, so let me comment out this one for a minute. Okay, so we're going to revert to some refactoring here. Right, so secondary space moves forward 24 because it's got to skip past the dictionary, the second word, and the start 2D. Okay, but if we didn't skip the start 2D, I think we could move it. We could move this up. Okay, but now that makes that makes the adjustment wrong here. Okay, because we've only really gone past 16 at this point. The first slot is 8. The second slot, add 8 is 8. Or first slot 0, add 8 to where you should be writing next. Okay, and so this one, it's there, but I think this should just be plus 8. Okay, secondary space. Wait a minute. Okay. I definitely have to move secondary space. So store system dictionary secondary space. Oh, system dictionary points to that. Okay. But I want to move secondary space forward. Well, I don't know. I'm being kind of artificial, right? System dictionary gets secondary space. And then I write into system dictionary plus 8 and system dictionary plus 16. But I haven't moved secondary space, so that seems unnecessarily complex. I mean, the system dictionary should point to that first cell of the header, and that's what it's doing in 36. But I think this is really secondary space plus 8, bang. Okay, so we're going to, well, wait a minute. Put a little dictionary at first slot. Store system dictionary system space. Okay, so that's the first slot. Secondary space points to 0. I'm going to modify it to point to 8 and increment it. And then I'm going to modify it again now it's moved forward, so I think it's the same thing again. Pound 8. Okay, so secondary should be yeah. I don't feel too bad about multiples of 8 in the address slots, when I'm doing things, but it is, yeah. Okay, so once we move the system dictionary to secondary space, I think secondary space should get incremented. Secondary space equals secondary space plus 8. All right, now, so it was at the first, it updated it at the first word, and now we move it to the next one because that's where it's supposed to be. And then these, well, they bear a lot of resemblance to something we made into a macro. Okay, so write this into the next slot and increment the slot, and then write this into the next slot and increment the slot. Okay, so by the time we get here, we've already incremented it 24, so I don't think this has to be done. Okay, let's make sure. Okay, so that rounds things off. Okay, we put the dictionary into secondary space. We store system dictionary at secondary space. And add 8. I mean, it's almost the system dictionary that should. Yeah, system dictionary's previous dictionary goes in the first slot. Yeah, that's why it's a little confusing. It really should be I mean, really, this would probably be better. Store, more consistent. Store that in there, and then I should say, um, add system dictionary. Well, subtract system dictionary 8. I should take that off, and then this goes away. Is that going to be right? So we store the dictionary, the old dictionary, into the current slot, move the slot counter forward. Then we want to say, where should the new system dictionary be? Well, it should be back one from where we were. So one way or the other, we're either going to add or subtract to get that consistent. But I think this is more, store this at this plus 8 in our secondary space. I think that's our macro that we already have. All right, let's see if this works before I blab on too much about it. Okay, so I think compile is probably the one that really needs to be tested. Okay, compile tests, semicolons. Yeah, so I believe we've done it. Okay, now this stuff. Oh well, let's see that macro. Where was that assembler? Store secondary register. Store register secondary space plus 8. Okay, so this can be used in here. So this is, oops, what do I call it? Store underscore sec. System dictionary. So write the system dictionary to the space. Okay, that should take care of this. Store sec x1 should take care of that. Store sec x0. Okay. Compile. Good. Okay. Whew. Well, all right. So what we've done is rework colon to update secondary, what do we call it? Secondary space. As it goes, use store sec macro. Okay. Yeah, that's a good thing. All right. Now, if you had a pointer to a word and you passed it into this chunk of code up to here, you would you have a good dictionary definition, and this is sort of the core dictionary stuff. It writes a string, it writes the first header slot, the second header slot, but not the third header slot. Okay, so I think this is well, I think it deserves to be a routine. So let's extract it, and I think maybe we'll call it define word. Define word and input x0 equals pointer to word string. And the effects are, well, effects, we store name word string to secondary, create first two slots of header, which is the pointer to previous dictionary and the pointer to the word string. And another effect is dictionary pointer All right, is there more going on? Yeah, I think that's about it. Okay, so I would like to make define word. Now this to me is just refactoring, but I'll try and do it correctly. So we need a standard prologue because we call stuff, and a standard epilogue because we had a prologue. All right. Now in here, X1 secondary. Okay. All right. We copy this. We'll do it the super safe way. All right. So the super safe way to me is we copy stuff and just make sure it builds properly before we start cutting stuff out. Okay. So I'll save and make. All right. Compile in particular. Yeah. Okay. Good. And then we'll define, we'll do the word. So this to here is now BL define word. Okay. Good. All right. And then I guess we need to make this a global word because we want to use it. Define word. Okay. Let's make. Okay. And we'll commit, extract, routine, define word. Okay. And I'm going to take this chance to get rid of these underscores. I just wasn't, it just didn't make a useful pattern. All right, so now let's look for underscore, colon. That one's okay, that one's okay. Well, this seems funny, doesn't it? Let's make this semicolon. So this is dictionary test. We got to make sure that still passes. And then semicolon. String. That's okay. That is not. Okay. And so it was dictionary tests. It was suspicious. Is metafines only matters? I think we searched for the same string twice, or we found colon in both cases, and it was a meta. So, all right, I think this will be better. Dictionary. Is metafines only metas? Okay, that's still good. All right, this is rename colon to colon, semicolon to semicolon. All right, and let's take that in our to-do. All right. Now we're ready to run this again. Search and replace. The cloud will tell you if you missed any. Yeah, I didn't want to do search and replace because so many of them were like L underscore semicolon this and that's really pretty legal. So I guess I could have looked for by word, but I just didn't trust it to catch them all. But that's okay. This should now fail again. We're back to our test. All right, so it doesn't get the right name. It doesn't get the right stuff. It doesn't find the dictionary. It's just no good. All right, but now in variables, this, because it's going to call things, it needs a prologue and an epilogue. All right, but we want to define, well, we're going to read word, and then we need to define, what do we call it, header? Wasn't compile. Define word. Oops. Okay, that should get us closer, but not done. We haven't done the stuff that's specific. Okay, global. Variable tests needs compile. It's more of a makefile issue, I think. Variable test needs compile.o. Define word compile.o. Well, those are in interpreter.o, I think. Interpreter.o. Data stack referenced from interpreter. Well, that's stack. Okay. All right, we got one thing done. We got our string pointing to is now name. All right, but the second one failed. Okay, so there's our first, whoops, there's our first assert. String was written to the dictionary, so it shows up there. Okay, now secondary space was adjusted to the right boundary. 8 bytes for the string, 3 cells in a cell for the initial value. Okay, no, it wasn't adjusted right yet. We haven't put the rest of the stuff in there. Okay, first cell is pointed to the old dictionary. That might be true. Okay, good. Second cell, we updated the dictionary pointer. That's true. 2 goods. Second cell is pointing to the new string. I'm surprised that's not passing. Dictionary points to there. Well, no. Dictionary pointer points to the first cell. Second cell should be that plus 8, isn't it? I believe. Third cell is system dictionary plus 16. Fourth cell is 24. And then we probably ought to assert, well, I don't need to TBD this, assert secondary space points past last cell. And secondary space, oh, no, we already did that. Okay. Okay, let's see if I got my offsets better. Okay. First one passed. Second one failed. All right, we didn't update the secondary space enough. We didn't put the value in. And we don't have the load address called. Okay. Now, in compile, right, we come back from define word, and we need to get the next address into the secondary. All right, so let's do that. But we need load address. Oh, we're gonna clean that. There it is. Okay, so we put load address in, and then I think we just need to store secondary XZR. So after we put the load address in, the actual value we want to do is a 0. Oh, we're close. Okay, secondary false at the end. All right, let's run that one. Variables tests.out. And since it's the last thing on that test, we'll just let it blow out. Okay. Variable writes header and values. Load 0. Assert equal. Move x1 0. Well, we got 1, 2, 3, 4, 5, 6 passes. How many do we have in here? 1, 2, 3, 4, 5, 6, 7. Okay, fourth cell contains the initial value. Oh, do I not need this? I'm already getting the contents of system dictionary plus that. Yeah. Good. All right. Added variable that reads name and creates a 0 and initial 0 value for it. Okay, now we don't have it in the REPL yet. Let's add that. Whoops, I lost you. Oh, sorry. Check data text and lines. Sounds like right to 0. Okay. Yeah, no, it was an extra indirect call here that did it. Okay, main. All right, now we have this new word, dictionary, variable, and it's a meta. So let's put it down here with the other. Maybe we should get all these metas together. This one is variable. And it's a meta and it calls variable. right, none of these routines look like they have underscores. Good. All right. Okay, so make REPL. Okay, so I guess what I think should happen is I define X. That should be good like that. Okay, now if I mention X, it should run the load address and come up with some memory sounding location if I print it. Okay, that sounds like it could be in memory. Well, don't you like this very critical test? Okay, creating a variable without a specific value. It creates a 0. Let's see, compile, no, variables. So our test made sure it contained a 0, and our compile wrote a 0 after it wrote the load address. So yeah, normally you would define a variable and assign values to it, right? But we don't have the operators for that yet. So that's our next task. Okay, so this well, this is good. All right. So let's see. So I think to be interesting, I mean that's something. That's behaving correctly, because normally what you would do, I mean, you would say variable X, and then X, you wouldn't do dot, you do at. And at is supposed to do the indirection and get you the value, and it should put a 0 on the stack. Should replace X with 0. It's not going to. Okay, we haven't defined at yet. I mean, this is actually helpful. All right, but yeah, at should take that pointer and look up what's in the cell there, which should be a 0, and then push that on the stack, and then the print should print 0. Okay, so normally when you use a variable, you do name at to get to it, and then name value bang to store something in it. All right, and I think, well, did I commit all that? No. Okay. Make, ACP. We add variable. I guess I could quote that. Variable meta word to the REPL. All right. Now, the next one is that operator, so it's the at operator. And well, at is pretty darn simple. It's going to take something off the stack and push something on the stack. Okay, so let's say test start at replaces variable with value. Okay, and I think again we can just do this with data. Get that straight. All right, so if we dot align P2 align 3. Okay, so if I make a variable, at variable, and let's give it a quad 42. And I never know when you have to do the pound signs. Okay. I suspect they're more optional than I've treated them as. All right, so now let's arrange act assert. Okay, so our arrangement is we want to push that on the stack. So we're going to do a load address. X0 is L at variable. And do a data push X0. I guess we got to do a stack in it too, huh? BL stack init. I don't know. Okay, yeah. So we'll initialize the stack. We'll push something on. Now we're going to call at, and we want to make sure the contents, data pop, oops, I don't know what I'm hitting. Data pop x0 and move x1 equals 42 and BL assert equal. Okay. I could use a test stack, but I think it's fine to use the real one. Yeah, I don't object to it here. We could set up a separate test stack, but I think we'll just call stack init and then data push and all that's happy. So, all right. So we initialize our stack. We load the address for the variable. We push it on the x0. So that's like variable name, that the definition we just did. And then the at is the operator we're testing, and data pop the value and make sure the value is right. So we should have the contents of lat variable, not the address of lat variable. Okay. And now variables needs the at method. At, and we'll just do a return. Okay, so that'll leave junk on the stack, the address on the stack. Did I say global at? I did not. Huh, I just realized we were using at and bang. Using bang for two meanings, so we'll have to be careful on that. All right, make. Quad. Stack init and variable tests. I thought we had stack. Oops, make file. Stack.o. Stack init is in stack. Oh, but it's called data stack init. Okay. All right. At fails its job. It basically has, we know that's a variable, and we expected a value. Okay. Yeah, I think, well, no, we're using percent for mod. I adopted too many C operators. Maybe, I don't know, maybe like an arrow or something, like dash greater. Yeah, $sign. My $sign might be okay. All right. This does not work. Let's make it. Data pop x0, load x0 gets contents of x0, and data push x0. And that's good old C's star. Good. All right. Now, well, we did this. At, okay, but store. Yeah, I think a little arrow guide would be good. All right, but let's get this in the main first. Okay, so at should be at. All right, so if I say variable x dot, I get that address. At, I should get a 0. Boom. Okay. Yeah, dollar signs usually for strings. At least that's been a pretty consistent convention I've been suggesting. All right, well, LDB dot slash rebel dot out. Load x0 failing where? REPL.out.at plus 4. Have I? No, I don't have any data there. Well, that does not look like a memory location. I will give you that. I was expecting at to take the address of the variable and then pop that and replace it with the contents of that address. So it would have the pointer to the fourth cell. So the first cell is the dictionary, second cell is the name, third cell is the load address, fourth cell is the contents of it. Oh, did I do that wrong? Yes, I did. Okay, you're right. So what was that doing? Oh, lilies. Sorry, I should know that word by now. All right. Let's do make REPL again. Variable x dot. That's nothing on the stack. X dot real address at dot 0. Okay. Yeah, that's better. I mean, it's basically that was a null pointer exception, right? Or, well, not null, but it was grabbing something off the stack that it shouldn't have, trying to treat it as an address and blowing up. Yeah, so I don't know if our underflow would catch that, but in general it would not, because you could have an arbitrary pile of stuff on the stack and then put another number on and do add on it, and it goes like, that's not an address, that's just a random number. Okay, yes, we're good. Okay, so good. Okay, so yeah, I think this arrow thing, I'll call it a sign. I could use equals. I mean, we haven't done, but I don't know. I think maybe arrow would be better. But I'll call it a sign. And we pop value, then pop address of variable, store value at variable, assign, return. Yeah, I don't know. I was thinking of just this for assignment. So you'd say name 7 assign. Maybe like add equals might be good, or equals at. Add equals. Name 7, take the address and set it equal to 7. I think I might do that. But we haven't written our test yet. Well, whoops, let's get that in the globals. Okay. Assign. How about stores A at B? Okay, so we'll create our stack. We got a variable. Push that. Now we'll push I guess I got to assign it first. X1 get X. Excuse me, X0 gets 27, and we'll data push X0. Okay, so and then we don't need well, what I want to do is do a load address X0 equals L at variable. Okay, so we'll load the variable and then we'll load its contents of X0. No, that's not right, is it? X0 is the pointer to the variable. Yeah, I guess that's okay. And then this should equal to 27. And that should be equal. And then I think I also want to assert this is right value stored to variable. And then this, well, I could probably just put my own guard on there. All right, so clear the stack, push 999 on so we can check it at the end, push the variable, push the value, do assign, come back and make sure the variable changed, and then make sure, I guess I'll say check that stack was popped twice. Okay, so both stuff should be gone. All right, this should fail. If I call it. Good. Okay, so we didn't have the right value in there, and the contents of the stack were the last thing we pushed, not the 999 that we put underneath. Good. All right. implementation. Okay, so we're going to data pop x0, data pop x1. So we pop the two addresses. I don't know. I find it easy to keep track of these when I do ones and twos, which is perfectly legal. All right, so we got the variables and the address. We want to do a store x1 at x2. Is that it? Okay, so we pop x1 is the value to store. X2 is the address of the variable. And then we store into the address. I think that's what it takes. Good. Okay. And we'll add to main. I think we can get some of this stuff out of here. That's assign. Make that, make REPL. Okay, so I do variable x. I'm going to assign x 77 at equals x at dot. So when I start x is 0, this should assign it to 77. It should print 77. Yay. Okay. Okay, good, good, good. What do we got here? And then somewhere we have a README. I think we put stuff in variables at, this is at equals meme, but this is at equals. I think that line might be better, the other order. Okay. Variables, no, this is not TD. Well, this is no longer TBD. We have repeat, we have if, else, and if, we have while condition do odd. This became V. We didn't do a for next. Okay. I believe that's all pretty accurate now. Yeah, it definitely is a little tricky. I mean, I remember at one point HP had a big line of stack-based calculators, and it was like the people using that were all the real geeks, you know. But you can understand why HP would do this because, like, not having to have parentheses really simplifies parsing arithmetic, and you know, you don't have to worry about a lot of stuff. You know, there's no everything is the order you put your operators, and not where you're going to keep a stack for parentheses and how you're going to match them up and all that stuff. So it's an easier model in some ways. And, this is PostScript adopted it for similar reasons. There are stack-based computers out there. Burroughs traditionally had them that used stacks a lot. And then for a while, there were RISC computers that they had so many registers because it's like, oh man, we got all this extra silicon now because we don't do complex instructions. And they would have registers that had kind of overlapping frames, and like your input values would be at the end of your register set, and then the new register set would come in and would lay over top of your input values and then its own register stuff. And it had kind of a similar feel as far as like allocating memory and all that. You didn't have to do I don't know. It just your high values on your outgoing, your calling thing turned into your low value registers on your input thing. And so it was sort of stack like that. I mean, call and return would slide these, they call them register windows over. But it's not common, and it is a mind twister. It's very easy to type. I mean, I've done it a bunch of times already when we were practicing, or like we were doing the repeat until tests. I kept typing something, blah, 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 minus space 1 instead of 1 minus, because I was putting the minus operator before the 1 and not after it. So it'll be a little bit of fun. Okay. Well, I think this is probably a good place for a break. We're going to come back and we'll do arrays, and they're actually very similar to variables. I think all we have to do differently is the initialization. I mean, all the rest of it is very similar, except initialization has to allocate a bunch of variables, a bunch of room, and fill it with zeros. Ideally, that's kind of a sop to making mistakes less common. But we want to do all this stuff the same, allocate a little more space, and then redefine these operators to basically do the multiplication and addition, so you get array access. Once we have that, we've got arrays done. So I think, we've got an hour. I think we'll probably finish arrays in that hour. Okay, so anyway, let's take a break, see you back in 3 or 4 minutes, and we'll pick it up from there. Welcome back. All right, let's do arrays. Okay, so we have to do array definition. We'll do plus at and plus at equals. Okay. So I guess this is still going to be in variables. Now, the declaration of an array is going to be a lot like the declaration of a variable. Header and values to a secondary. Okay, it's going to be similar setup. So we'll set up a space for it. We'll override the read words routine so we get it. Does read words... Well, I don't know. So we need to be able to say name, array, name, number. And so my read words here is not really so good at doing that. x2 equals number of characters max to read. I don't know how that'll do. We might be able to x0 equals variable test input string. No. Size goes after the name. Right. So, well, let's get this. Let's get the pieces we can, and then we'll worry about the rest. Okay. BL variable. Let's BL array. Okay. The string was written to the dictionary. Yes, that's the same. Secondary space was adjusted to the right boundary. Well, that's gonna change. Okay. So this is 32 plus the values. We somewhere need a way to make more input strings. Let's just do 3. Number test string final. Okay. If you put it before you can calculate the size. Well, that's true. Oh, so you're saying like 42 array name and 42 goes on the stack? That's kind of nice. Yeah. Okay, let's make that our plan. So we'll say size array name where size is the value on the stack and array is a meta word. Okay. And let's modify that over here. I don't think I mentioned arrays yet. No. Okay. Yeah. Oops. And variable tests. Okay, so I don't have to do this screwy stuff on the stack, on the reader. Good. Okay, I think this sort of information might be useful though. Okay. Variables, tests. Okay, so this is the name string, the pointer to the dictionary, the pointer to the name string, and then I'm going to make this 3, so 48 is 3, and 56 is open. Okay, so we're going to do a data push. Okay, which means I got to call data stack init. Okay, oops, 3. Alrighty, so I'm going to write in the secondary area. That's all the same. We call array. The string should be written in there. It's at slot 0 plus 3 times 8 bytes for the variable's initial value. That's 1, 4, 7. What was it before? 1, 4, 5. 7 times 8 is 56. Okay, that's right. So secondary space should be pointing after our 3 allocated stuffs. Okay, first cell is pointed to old dictionary. That's true. Dictionary pointer is updated. Yes. Second cell is pointed to new string. Yes, that's true. Third cell points to load address. That should still be true. Fourth cell points there. Okay. I think we can just continue those assertions. Okay. Fifth cell is 32. I feel like I'm off. And sixth cell is 40. So why is that not 48? 224 are part of the act, I think. 224. Yeah, I guess you could see it that way. Yeah, we can do that. Okay, because it reads its own words, so that's already kind of there. All right, now why am I inconsistent on 56 versus 48? Okay, so x plus 0 is the string. X plus 8, 16, 24 are these. 32, 40, 48. Why am I not counting right? Three header cells, right? 1, 2. Wait a minute, that can't be right. Oh, I'm going off System Dictionary. Okay. System Dictionary is 8 bytes bigger than that. Okay, so 40, 48 would be the contents off secondary address as starting point. Okay, I think that's right. And if I call that routine and put an array thing somewhere, all right, good enough to fail, I hope. Good. All right. Array writes header and secondary values. Well, I don't know why that would pass per se, but let's look at that test. Okay. So the first one is the string got written to the dictionary. Really? How did it? I hate it when things fail that shouldn't, or don't fail when they should. All right, something is strange. The offsets. Yeah, I think what it is the system dictionary points. So secondary space started at slot 0, and that contains the word name, and then system dictionary starts at slot 8, and so all our offsets are from system dictionary. So when I do 40 here, that's really 48 off the secondary space, and then secondary space should point after this cell, so it's 56. So I agree, it's a little weird. Maybe we can work on a better explanation of that, but I think it's correct. But I'm very puzzled why secondary space got adjusted. Oh, it probably. Assert equals strings. L test secondary area. L test secondary area. Oh, I think maybe the old one got it. I think because we ran the old test first, it was lying around. Let's stop this one. Yeah. Okay. A little unfortunate. I think as the others go, it'll be right. Okay, because I think we could almost. I mean, everything in variable, right, is the stuff we want to do. Read a word, define it, put in the load address, and then store secondary 10. Well, that gets us one of our cells, but we don't have the rest filled in. But this this should be enough for most of that. Because there's mostly no difference between them. It's really the operators that are going to do the different work that'll do the array offsets and stuff. So I think this should pass more lines. Okay, yeah. So it doesn't pass the secondary space pointers should be, is that 16 bytes further? That makes sense. Yeah, 24 and 6 is 30, so 16 bytes. So we only appended 10, but we really need to append 1 for every value on our stack. Okay, so I think when we get back, now that we've got that defined, secondary space is ready for the next thing. So at some point, I mean, we basically need a counter. Let's do data pop x0, and that's the number of cells. Okay, and then I want to do a while loop. So I want to do while the number of cells is not 0, although I could even do 1. But while I don't need more cells, I'm going to put this in pseudocode. While need more cells, I'm going to do a store of 0. Well, I guess I can do my sec store 0. Odd. Okay. Well, I'm going to do sec store 0, and I also need to decrement my x0. Subtract x0 gets x0 minus 1. Okay, and so the check is, well, I also need to subtract, I've already written 1. We wrote 1 cell with the variable, so I really need n minus 1 cells. Okay, and so this is array loop. Okay, and then down here is jump array loop. And this is array after. Okay, so we're going to do a compare x0 to 0. And if it's yeah. If it's equal, we're going to go to array after. Okay, does that make sense? Okay, so I guess the alternative is I could compare to 1. But I think this will check the right thing. All right. Well, JMP. Oh, that's branch. Sec store sec. Well, store sec xzxr x25 pound 8. Is it xzr? Am I messing up my? Yep. Okay. Oh, variable array writes to header. Okay. Well, that's good. Yeah, I pre-decremented. I don't think it's any worse one way or the other. This loop is right, n minus 1 zeros. Okay. That should still pass. Okay. Yeah, let's do that. So we start off with, let's say we said 3. We've got 1 already. We'll subtract 1 from 3. We need 2. Are you 0? No. Right. Come back. It's 2. Subtract 1 is 1. Are you 0? No. Right. Come back. Subtract 1 is 0. Yes. Exit. Okay. Should be the same. Saves us an instruction. Always good. Oh, darn it. Let's do a make and make sure it's right before we commit. Okay. A little out of order, but that's okay. So we need a main word for that. And we have variable up there somewhere. There it is. Okay. Three array X. Now I can do X dot, I'll get its address. Okay. If I do X, I've got X on the stack, the address. If I add 8 plus, that should get me to the second cell. And at should be 0. Well, at, yes, should be 0. Okay, and then I can do X 8 plus at equals 7 dot 7. Oh, boom. What was that one wrong? 8. I have X on the stack. Push 8, add to it. Do at, I should get the second cell. All right, do X on the stack, 8, add to it. Add equals. Well, I thought it should. I mean, X plus 8 is a valid address inside that array. Oh, 7 equal. Okay, I screwed it up. Okay, so 3 array X. And then if I do X8 plus 7 add equals, I should write a 7 into that cell. And if I do X8 plus at, I should get the 7 out. Great. Okay. Just to know 99. Yeah, so it does work. That gets me cell sub 1 because 8 times 1. All right. Which is good. All right, so we've got array, add array to REPL. Okay, and now we want to make the variables we want an array focused assignment, basically. Okay, so let's test. Well, wherever at is going to be pretty similar. I'll maybe call it at array. Array at. Replaces variable with value. Okay, so we'll clear a stack. This one, we need to push the variable, and then we need to push the am I getting this right? Add variable. Well, I think we have to create it first, right? Is that true? No, it's not really true. Add variable. Okay, let's. You know, these things 42, 3, 2. Keep them shorter and simpler. Okay, so in effect, it's an array now. At doesn't care, but array at will. Okay, so the value on the stack, the first value on the stack should be the variable. The second value should be the index. Divided by 8. X0 gets 1, and then data push that. X0. Let's call it X1. Okay, so we push the address of the variable on the stack, and then of the array in effect. Then we push the value 1, and we want to get array at. If you call that, then the value should be the second value, which is 3. Let's change the order of those. Let's make it 2, 3. Okay, so that's array sub 0, that's array sub 1. We should get a 2 back. That value, variable, and index with value. Okay. Now we can do our trick from last time. Move x0 gets 9099, and data push x0, and then we'll assert that that's the next thing down. Okay, and this thing doesn't exist. Well, this needs to exist first. Let's call that. Okay. And then this goes in variables. Array at just does a return. Address plus 8 times index. Keep the size of the array. We don't need to. I mean, you could. Can we directly tell? I don't think we can directly tell. We're relying on you not to bust it. We could add those protections, but I'm not going to, I think. I don't know. I mean, real life, I mean, like C doesn't do it. You can get by with that. Yeah, you don't. So yeah, if you say create an array of 7 cells and put something in cell 10, it's just going to throw that into our secondary space and overwrite something. So you won't know, but you certainly, usually when you're doing this, you're going to write some sort of loop or something and not exceed that value. I guess you could put it in a variable if you wanted to, to have that maximum size in. So I'm most of the time when I take these shortcutish things, I'm willing to say I'm reaching for a C level memory model, not a Swift level memory model. But in Swift, we would keep track of that array size and be very careful that they didn't exceed it or, go underneath it or something. They'd have to be in the range. Again, if this were a language I was seriously using for a long time, I might be more tempted to enforce that stuff. But it does cost you. You know, we'd have to check that this value is greater than 0 and that it's less than or equal to this memory size, or less than this memory size address plus the memory size or something like that. So, I mean, 4 or 5 instructions, you know, with a loop test and maybe a call to a crash function and all this stuff. It's some overhead, you know, for what's going to be a handful of instructions. So I'll let us pay that price in debugging time. After we do it for a while, I may go like, you know, this is just happening too much, and let's put a check on it. I suppose we could probably define an access method that took a size variable and a counter and the index and all that, you know, something like that to enforce it. Okay, that's done in array at. Array at. Make. Okay, x1 equals 1, x2, x0 equals 1, 2. Okay, so it did not find the right value, did not pop the right value. And it didn't keep this in the second place. It didn't do anything. So it left 999 variable and 1 on the stack, and we're not finding them in the right order now. Okay, so implement it. Well, let's look at. I'm just going to steal it. Okay, data pop the index. And we need to pop the variable. Then we're going to load x0 gets. Well, I think it's x1, x2, LSL3. If I remember my modes. Okay, so let's find them. That's in environment notes. I put the carry stuff in, but yeah, this one, register shift with offset, RA plus RB times 2 to the nth. So LSL3 gives us 2 to the third is 8, and it multiplies those. So this is exactly the kind of thing we want. I hope LDR supports this mode. All right. And what do we do in variables? Then we looked at the value there and push it. That seems pretty good. And just to kind of consistent there. Hide you for a bit. All right. Oh, boom. Okay. Let's LLDV variable tests out. Oh, did I use x1, x2? x1 is the index. x2 is the address. Much better. Okay. And, okay, that's array at. And our main. Okay, so I think we can do the same thing we did before. Okay, so say 3 array x. Let's use A. Okay, now if I do A on the stack and then 1 at dot, I should get a 0. Okay, let's do it again and use the right operator this time. 3 array A1 plus at. Maybe at plus? I don't know. Plus at dot should give me a 0. Okay. I don't know. I guess I could do A 16 plus 7 at equals. So that would take A plus 2, store a 7 in there, as if it were a simple variable. All right, and now if I do A2 plus at dot, I should get the 7. All right. Okay, so ACP added plus at to REPL. Could have a fill command where you push in values on the stack and then in. Yeah. Let's keep that in mind, because I think when we start using it, we're going to have stuff like that we want. Something like that. I like it. Okay, next test. This is going to be very similar to the test for checking the contents assigned. Array assign stores well, how does that one work? Pop ABC. Okay. Stores A at B indexed by C. Okay. Clear our stack, push a guard value, push the variable, push the value to assign. We need another push. Let's use index 2. Push the index on the stack, and then the value to assign. Is that consistent? A is the value assigned, B, C is the array, B is the index. So we push the array, the index, and the value in that order. Okay. This is array assign. And then this 0, 1, 2, x1 plus x0 plus 16 accesses off it. Okay. And I think we'll see a 3 there now, not a 27. And pop the next one, and that should be It popped 3 times. Okay. And this doesn't, well, this test needs to be called. And he's calling array assign. Okay, so we get a 3, even though we expected a 27, because that's the value that's there at that slot. And then the 27 instead of the 199 because nothing got popped. All right. Okay, so variables. Well, once again, assign is going to be very close to array assign. Data pop x1, x2, and x3. Store x1, yes, at x3 plus x2 times 8. All right. Woohoo. Let's check that in. Make array assign work. Add it to main. You know, I think at plus is going to read better to my mind. At plus equals array assign. Nope. I don't think that, well, it changes documentation, but it doesn't change anything else. Okay, so we need at plus well, a equals mem sub a sub I. Let's say it that way. A sub b. B sub a. Mem sub c sub b equals a. Okay. Did I build? Okay, we put them in main. Okay, so 3 array A, and then if we do A sub 0 equals 20 at plus equals, and then A sub 0 at plus dot, we should get 20. Okay. I like it. Cool. Well, I mean, that's kind of interesting, right? It took us 45 minutes to add arrays to our language once we had variables working. A little longer to do the variables, but they were, well, basically from 2 to 3:30, so an hour and a half to do the variables, followed by an hour to do the arrays, or 45 minutes to do the arrays. Let's push this. Add at plus equals to REPL. Okay. Well, we have 10 minutes, so let's look at our next thing is really strings. So again, we have these multiple parts. We need something to do creating a string and put an address on the data stack. Now, like once you have that address, I'm going to say strings are immutable. You can index into them and get a substring, the tail of a string. But we're not going to keep track of, oh, this string is no longer used. So there's a little bit of a memory hit in that. And I mean, it only shows up when you're constructing strings. So that's pretty good. I guess split, I should make a join. Ugh. Join pop address of A, of B, then A, create string, create concatenated string, push address of new string. Okay. Yeah, I mean, that's the one that's going to be expensive because it's going to ignore existing strings. If you use make $, that's cheaper in a way, right? You can fill up all the characters and then convert it in one bang. You don't have to, you're not creating a new string. You're reusing this array until you're ready to fill it in. So yeah, okay. All right. So I think our first thing in there is string, quote string, needs to create a string and put an address on the data stack. Now, I guess the only thing is if you're in compile mode, well, if you're in execute mode, that's perfectly sensible. If you're in compile mode, like should you have to? I guess I'm not going to worry about it. If you are foolish enough to create a loop, or if we are foolish enough to create a loop and put a string creation in it, that string will get allocated. Well, that'll be an issue. We'll have to think about that. It'll get allocated and reallocated, or what happens to it? I'm not sure. All right. Okay. So, well, we know how to start this stuff. So let's take a look there. And you know what? I think what we're going to see that was in compile, right? This same action, put the word after this and then adjust the space, is kind of the same thing we want to do for a string. Okay, so I think let's do a refactoring. I don't think this is too weird. I think given x0 points to a string, we should copy it into secondary space and update the secondary space pointer to point after that, getting back to a 64-bit boundary. Regardless of string creation, that's going to be something we need. So that's a good refactoring. Maybe that's a 10-minute refactoring. All right, so we're going to define string. Input is x0 as a pointer to a string. And the effect is, store word string to secondary. And adjust sec space to a 64-bit boundary. Okay, and then define string, and we'll make it global. And then really these two should come down. Okay. All right, so define string, well, it's going to call stuff, so it needs our standard prologue. Well, it actually just needs this, right? Try again. There we go. Okay, standard epilogue return. Okay, so we start writing. X0 is the string input string, X1 is the output place. We're going to start writing to a sec space, and then we will increment sec space by string length. Okay, a little bit of overhead there. Yeah, exactly. Now, whether we treat it, we could define an array dollar, that's an array of strings, or we could. There's probably a way to, with the stuff we have, we might be able to just treat it like that. Yeah, not worry about it. Not worry about the LSL3 we did. Okay, are we done? So, string copy the word, get the length, and then we add 8 and it together, so we chop off the last 3 bits. So we move the pointer forward and then chop off the last 3 bits to make sure it's on that 64-bit boundary. And I think move X1, get secondary space, add secondary space X0. I'm not quite sure what that's doing. Move X1 gets secondary space. Well, we're taking the string length. Oh, this is just, no, wait. We haven't adjusted secondary space until there. But X1 is the old value of secondary space. That seems like it's on you to keep that around. 61. Yeah, he needs that pointer, so he needs to know where we stored the word. So I think before this calls store, we need to save. We'll need to create a temp variable to hold it in while it does all that. Okay, but I think this gets you. Well, I think this Yeah, none of this changes secondary space until you get here, but we need this line to come up top. Okay. Right. Okay, but he's going to be x28. So let's find an x28. All right. So somewhere yeah, there we go. So x28's a caller save. So we're going to use it. So we got to save it first. And then we're going to do this in x28 instead. x28 gets secondary space. This goes away. This needs x28. And then we need to restore that. At the end. Okay, I believe that should have no effect. You start writing secondary space, copy, blah, 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 and change. Okay, but I don't think I have this line up there. Okay. All right, now we're not calling the new thing yet, so it certainly shouldn't have an effect, I hope. All right, okay. Good. Okay, so now this move x1 secondary space. This stuff is all define string. And secondary space. Yeah. Okay. Okay. Yeah, I think that's true. And make. All right. And I'm sorry, what test are we in? Compile? Yeah, let's make sure compile particularly. Okay. Yeah, good. Okay, so let's save that. Extract method define word. Okay, define string. And that'll help us out tomorrow. So tomorrow, 2 to 4:30 Eastern Time or 6 to 8:30 p.m. UTC, I'm anticipating we finish strings, and we'll then take any simple looking bits that we can do. Well, we'll finish string creation. I don't know if we'll finish all these methods, but we'll start them. And one way or the other, we'll make progress on them. Okay. I do want to do this before we give up on the compiler, and I'm looking around to see if I can find information how to read a raw character. If you run across something that tells that, let me know. We can get by with reading a line like we do for the REPL, but I really, really would love to read a single character thing so it can make a little more sophisticated applications. Okay. That's it. See you next time or some other time in the future. Take care. Good night.